A resonance structure is one of two or more Lewis structures for a single molecule that cannot be represented accurately by only one Lewis structure. This is ozone. Notice that a double bond is used to complete the octet. In the first case, the double bond is between the first and second oxygen. In the other case, to the right, it's between the second and third. These are resonance structures. Both are accurate. There are exceptions to the octet rule. The first is the incomplete octet. Beryllium hydride is an example. Beryllium has 2 electrons. The 2 hydrogens have 1 electron each for a total of 4. If we connect the hydrogens to the beryllium, we use up all of the electrons, leading to this type of molecule, a linear one. Boron trifluoride is another example. Boron has 3 electrons. Each of the fluorine have 7 for a total of 21, plus the 3 is 24 electrons. This is the Lewis structure. The octet is fulfilled by each of the fluorines, but the boron is short a pair of electrons. 3 single bonds, 6 electrons, and 9 lone pairs, 18 electrons for a total of 24. We have this resulting planar molecule. Odd electron molecules. Nitric oxide is an example. 5 electrons for nitrogen, 6 for oxygen. Total is 11 electrons. The best we can do is this structure. Again, we're short electrons on the nitrogen. It cannot fulfill the octet. The expanded octet, where the central atom's principal quantum number is greater than 2. Sulfur hexafluoride is an example. Sulfur has 6 electrons. 6 fluorine bring in 42 more electrons. If we attach them all, notice that the sulfur has more than the octet. The 6 single bonds account for 12 electrons. The enthalpy change required to break a particular bond in 1 mole of gaseous molecules is called the bond enthalpy. Look at this table here. Hydrogen is broken into hydrogen atoms. That takes 436.4 kilojoules. Chlorine broken into chlorine atoms, 242.7. Breaking the bond between hydrogen and chlorine, 431. Breaking the double bond in oxygen, 498. Breaking the triple bond in nitrogen, 941. In general, the triple bond enthalpy is greater than the double bond is greater than the single bond. More bonds, more energy to break them. Here's a table of bond enthalpies of some diatomic molecules. Use bond enthalpies to calculate the enthalpy change for H2 plus F2 making 2 moles of HF. In this case, the change in enthalpy is going to be equal to the sum of the bond energy of the reactants minus the sum of the bond energy of the products. If we break the hydrogen-hydrogen bond, that'll cost 436.4 kilojoules per mole. The fluorine-fluorine bond being broken is 156.9 kilojoules per mole. When we form the bond, we have an HF bond. There are 2 of those, so it'll be 568.2 kilojoules per mole for each bond, or a total of 1,136.4 kilojoules. Adding up the bond energy of the reactants and subtracting the bond energy of the products, we arrive at an enthalpy change of a negative 543.1. The energy is released.